We're starting lecture 18, which is boiling. We'll go through it and let's see, review first what we did last time. So just remember last time we were talking about what we call free convection or natural convection. The idea is that you have these density gradients that lead to velocity. And that velocity causes heat transfer, convection to occur. Boiling, like what we're going to talk about today, is actually closely related to natural convection. It's just that you have a phase change that's involved, not just a single phase fluid. So, okay, we can go through and we can calculate the characteristic velocity based on this term that involves gravity and the volumetric thermal expansion coefficient, beta. It also involves the temperature difference, Ts minus T infinity. There's a Grashof number that's just Reynolds squared for this problem. The Rayleigh number is Grashof times Prandtl. So the only real difference here is we could say Rayleigh number here is basically the same, but you're multiplying it by nu over alpha. So in the full written out expression for Rayleigh number, you would just have nu in the denominator times alpha. So that was also on a discussion problem, I think. There's correlations for this, and then we also talked about this idea for combining convection. So if you have forced and free convection, that is natural, forced and natural convection, or you have two correlations you're trying to merge together, you can use this approach generally, where you choose M based on how much you want to weight one versus the other, right? How much you want to sort of force the solution to go right away to one of the two. Okay. So then, boiling. I actually kind of like this topic because there's like a lot going on and it's kind of an interesting process. So we'll go through and we'll talk about two different types of boiling that are commonly encountered. So one is called pool boiling. Pool boiling is when you have the only motion is due to local density gradient. So it's very much like natural convection. You have like, you're generating, let's say you're boiling water, right? You have a pot of water, you have a bubble that forms. That's a local density change. That causes movement of the fluid. So it's very much like natural convection. Flow boiling, on the other hand, is where you have the phase change occurring, but the fluid is being forced in one direction. So both the liquid and the vapor phases are together being forced in one direction because of a pressure gradient that's involved. So those are just general definitions. The other thing that's a little bit different about boiling is usually we talk about this heat flux or heat flow. So let's say heat flow into the fluid. This is defined usually as Q dot double prime, same as before, at the surface, S, is equal to H bar times delta T sub E. Okay, so this is a little different. Delta T sub E is something called the excess temperature difference. Excess temperature difference. And this is defined as delta TE is equal to, delta TE is equal to TS minus T sat. So TS in this case is the surface temperature. T sat is the saturation. All right, because you're changing phase here. You're going from liquid to vapor. So there's a saturation condition. That saturation temperature is what's really driving this. So like if you combine these two things together, you take that Ts minus T sat, it looks a lot like our previous definition of heat flux for convection. It's just that we're always defining our kind of sink temperature, our cold temperature, as the saturation temperature. That's like the coldest that you can get in this particular system. So really what we care about in boiling is controlling this Ts. Right? You're wanting your system to not basically overheat. All right? So some things to maybe say about boiling. Typically, like if you are constructing a boiler and you do it in a careful way where your boiling is what's called nucleate boiling, you don't really have to worry too much about the resistance due to boiling because it turns out like phase change is a really, really good way of moving heat. So if you're boiling and it's in a certain regime, the heat transfer coefficient, this H, is so high that it is almost always negligible in your resistance network. Okay, but it's not always the case. If you start developing like a layer of vapor, we'll talk about that next, then you can get into trouble. So typically like boiling and condensation processes have really, really high H values, and so you can support, for a relatively small delta T, support a really large heat flux, okay?